Okay, after the first investigation, you learned that in a right triangle, in an isosceles right triangle, the sides opposite the 45-degree angle, we already know that they're equal, so I happen to use the variable a, and then the side opposite the hypotenuse, or the side opposite the 90 degrees is a root 2. Okay, so we're going to use that, and the reason I use a is just because I don't want to mix it up with x in case x is in a funny spot and it doesn't, you get two x's. So I'm going to do that here. So we know that this is 45 degrees and this is 45 degrees based on the base angles theorem. And so this and this, a is x, and we know it's isosceles because the two sides are both x. So you could call it a or x if you wanted. Okay, and then this c would be a root 2. Okay, and that's what it's saying in the theorem. Let me. So I just cleaned it up a little bit there so that we could do some work on it. And what you'll see is we'll use the Pythagorean theorem to prove this. So we know c is c squared. We know we'll call this a and we'll call this b. So a is x, so I'm going to change it to x squared, and b is x, so I change it to x squared. C is c squared. So you ask yourself, how many x squareds do I have? I have 2 of them. And if I'm really interested in getting c, not c squared, so to undo squaring, I square root, and we're only interested in the principal square root because negatives don't make sense here. So I get c, and here I get root 2, and I get the square root of x squared. And it turns out the square root of x squared is easy to deal with. That's just x. And the square root of 2 is the square root of 2. And we've just shown or proven deductively using the Pythagorean theorem, up here, we've just shown that yes, and indeed, if you have an isosceles right triangle, no matter what the side length is, remember the two legs are the same in an isosceles right triangle, you always force the hypotenuse to be whatever the side length is, whatever the leg length is, times root 2. So this would be a proof for it.